water part, so the close cooling water, the cooling water with your ACC, the air-cooled condenser, etc. One part here from my side, everything which is in here is not a Siemens standard. And I think it's not everything delivered by Siemens. We're doing this training to support you as the operators over there, but it's not a Siemens component. Yeah, so it's coming from I think a Chinese manufacturer. So we putting it here together to provide a training for you and giving here training information. Yeah, let's say all the information we're getting, but it's not a Siemens standard boiler or water steam circle or cooling water system. Yeah, so there are some differences in. So for me, it's also some things are not standard. Yeah, let's say like I know it from Siemens power plants before, but we will try to get there the best information for you out that you know, okay, that's how it's looking on my power plant over there. Oh. So starting with thermodynamics and physics, yeah. So in the general part, first of all, most important, let's say, is here an overview, basic diagram of an combined cycle power plant, it's a CCP. Combined cycle, meaning you have on one side gas turbine cycle and on one side the steam turbine power plant. Otherwise, it would be an simple cycle power plant. It would be just a gas turbine, yeah. Or you have probably an coal power plant, and you have here no gas turbine. You have here an boiler, yeah, where you're burning the coal, and then you have here over here the steam turbine. So it's split up on a combined cycle power plant, gas turbine, the boiler, and steam turbine plant. Steam turbine plant is here mainly, let's say, the water steam circle part. We have the boiler part and then the steam turbine. So this is our total water circle. On the left side, we have the gas turbine. Gas turbine, of course, consisting of the gas turbine air intake. Yeah, so we have the big air intake system with filtration in that we're getting only clean air into the turbine. We have then over here the number 2, that's our compressor. The compressor is compressing the air to 13, 14, 15 bar pressure, yeah, to increase the volume over here, which we're getting into our combustion chamber. So in the combustion chamber, there is the burning process happening, mixing from fuel and air. I mean, for the basic, you know, you need a certain amount of fuel with a certain amount of air with the right amount of fuel and air. There's a burning happening. When you have too much fuel in there, the burning process will not happening. When you have too much air in there, the air will blow out the flame. Yeah, so you need the right relation between fuel and air that the burning is happening. And then inside the combustion chamber, you have here temperatures up to 12, 13, 1400 degrees Celsius. And from there, we're getting through the turbine part of the gas turbine. And the gas turbine over here then has normally 4 blade rows where we're taking out the power from the fuel air mixture, yeah, from our gas. In this process, the exhaust gas temperature is dropping. Yeah, we're doing work over here on the rotor. Yeah, the temperature is dropping. The energy is absorbed into rotation energy, and with this rotation energy, we driving our compressor and our generator over here and producing an electrical power output. The power generated over here in the turbine part, 50% will get into the compressor to run the compressor. So there's a high amount of power used just to run the compressor. But without the compressor, you cannot get the power output over here. You cannot get the temperatures for the burning over here, and then it's not working properly. Yeah. So with the generator over here to a transformer and then into the electrical grid, where the electricity is then going to the household or the industries who need the electrical power. On an open cycle power plant, simple cycle power plant, you would now just send these hot exhaust gases into the air. But on a combined cycle power plant, because we have here hot exhaust gases with 500, 550, 600 degrees, yeah, and we said there's a lot of energy in this exhaust gas, so we will use this energy. And this energy we will use with within the boiler, so there are pipes in there which are heating up, producing steam, and then we will get steam out here, which we can send onto the steam turbine. In this case, the steam turbine is an 3 pressure stage turbine. Yeah, so we have here the HP high pressure part, we have the intermediate pressure part, and we have a low pressure part. That's depending on the turbine configuration. Can also be HP and LP only, that you don't have an intermediate pressure part like you have it in Shatt Al Basra. So for the water steam circle, we normally always starting on the outlet of the condenser. Yeah, so we have here getting water in, we have a condensate pump in, getting over here the condensate to the feed water pumps. The feed water pumps increasing our pressure for the whole water steam process part over here. So we increasing here one time the pressure, and from there then let's say getting into the boiler with the feed water. This is just an basic diagram. Of course, on the power plants, it can be always a little bit different. It can be that for LP pressure, where you have normally 4 or 5 bar, that the condensate pump pressure is enough to get it into the LP drum. Yeah, over here it's shown that it's getting off from the feed water part. Yeah, can both be. It's just a general drawing. So we're getting into the boiler part. In the boiler, we have normally some preheaters preheating the system. In detail, we will go on your power plant later on when we go through the system. So general process for producing steam is we have one time for preheating. We have then an evaporator, yeah, so where we're producing our steam. And after the evaporator, we have a so-called superheater, where it's only steam in, and then getting the steam, for example, here onto the HP part. So in the preheater, we just want water, we don't want steam in there. In the evaporator or the drum, there is steam and water in, yeah, so we bring water in. With the temperature, we will produce steam, and the steam will be separated then within the drum, and only steam is getting out to the superheater. And in the superheater, of course, we only want steam in there. So from there, we're getting into the turbine, yeah, leading into the turbine. In front of the turbine, there are, of course, emergency stop valve and control valve to protect the steam turbine. And in case the steam turbine is not running, or the steam values over here are not sufficient yet for steam turbine operation. There is a bypass station in, and the bypass station is bringing the steam around the steam turbine. In this case, because it's a 3-pressure line, the steam from the bypass station is getting here on the so-called cold reheat line. On a 2-pressure circle, it would go directly into the condenser. So here in the 3-pressure line, getting back to the boiler, we using the outlet steam from the HP part of the steam turbine and sending it back to the boiler to reheat it again to bring it onto the so-called IP turbine part, intermittent turbine, because the IP turbine can handle then, let's say, at least the same temperatures. We have a higher energy input again and can get a higher power output from the steam turbine. From there, from the IP part, at the end of IP, there's still a lot of energy in the steam. We have normally pressures around 5 bar on the outlet of the IP turbine, and then getting mixed with the LP steam and bring it onto the LP turbine. Of course, IP bypass station, there would be also an LP bypass station over here, which is here not drawn in. So this would be the LP bypass, which is of course in there, which is not drawn in this basic diagram in, but of course it needs to be there when there's no steam taking from the turbine. Then we need to bring the steam somewhere safe, and the safe way is then the condenser. So over here, when steam turbine is running, of course connected to a generator, and then with the transformer to the electrical grid. So the steam from the LP turbine outlet is getting into the condenser, and inside the condenser we need to condense the steam, and in this process there's a lot of energy getting free, so the so-called latent heat, which is warming up our cooling water. So we're getting here in this example fresh water in, with the cooling water pumps. The cooling water is getting in and taking the latent heat away. So our condensation process can happen over here. Inlet temperature, I don't know, probably 20 degrees, outlet temperature 25 degrees, and then it can be sent either back into the river or the sea for freshwater cooling. You have the chance cooling tower in when the temperatures are getting too high for the outlet, that it's not allowed to bring it back into the sea. Or you can have here an closed cooling water circle, let's say with an ACC, with an cooling tower, to cool down the steam. Or you don't have an condenser over here and you bring in the steam directly to the ACC, and you don't have a cooling water system needed in this point. This is for regions with pretty small water amounts, where you have this steam directly getting inside an air-cooled condenser. There are some fans in cooling, and the big advantage is you have a closed circle over here, so you're not losing any water from your water steam circle. And then you bring in the water back to the condensate pump, and the circle is starting again. So this is now the basic overview over the combined cycle plant. Main steam temperatures in this example, let's say 565 degrees and 125 bar, can go up more on newer power plants where we are at 600, 610 degrees and probably 180 bar, yeah, for combined cycle. The higher you go, let's say, the more power you can get at the end out of the steam turbine. We have then here the cold reheat line, yeah, with 350 degrees and 32 bar. The hot reheat 565 again, yeah, so the going back with 350 degrees into the boiler. We're heating up the system again to 565 degrees and then bring it onto IP turbine, and here LP induction steam is around about 4 bar. So that's the general overview of the combined cycle plant. And then in the next step, other questions from your side, or this should be clear, I think, so far, yeah? So then in the next sheet, we have over here, let's say, thermodynamics and physics, yeah, melting and vaporization, yeah. So we seeing here one time our temperature. So this is from, let's say, minus degrees to 0 degrees to 100 degrees. So normally melting point of ice and then, let's say, boiling temperature of water. And on the x-axis here, we're seeing the quantity of heat. So that's the amount of energy we need to put into the process to get here either boiling water, to get the ice melted, yeah, and then this melting temperature, yeah, where the process from ice to water is happening without any temperature change. So we're starting over here when we have ice, let's say we need a pretty small amount of heat to get it to 0 degrees, yeah. So when we have ice with minus 20 degrees, we take it out of the fridge and it's like the ambient temperature is 30 degrees. You can see the ice will start melting pretty fast, yeah. The energy for the melting process is over here. It's pretty small, yeah. So when you have an ice cube over here, you need a pretty small quantity of heat to put it in to get at this point water with 0 degrees temperature. And this is something, let's say, which is not happening or hopefully not happening in our power plants, yeah. Because let's say as soon you have freezing somewhere in the power plant, let's imagine your power plant at winter, let's say in Germany, you're getting like minus 10 degrees ambient temperatures and you have some pipes outside where water is standing in and they start freezing, yeah, and then you have big problems in the power plant. And this, of course, we want to avoid. So there will be heatings on there to make sure that the pipings will stay over 0 degrees so that the water inside will not freeze. The main reason for it, when water is freezing, the volume will increase. And when the volume will increase and you have a certain amount of water in a pipe, yeah, so you have, let's imagine you have your pipe in here and the pipe is filled with water, yeah, so there's fully filled with water. And now the temperatures here outside, temperature less than 0 degrees Celsius. So what's happening? Our water inside here will start freezing from the outside. The volume will increase, and then our piping in most cases cannot handle the amount of volume, and then the piping will burst or open up. Yeah, so we will have a leakage over here, and this, of course, we want to avoid. So the avoidance in this case is, when we say we're putting this one away. So the avoidance is we have some heating over here. So that's normally some electrical wire where we're sending electricity through. So it's a trace heating, and the trace heating is switched on, and then making sure that you get there a certain temperature inside the piping so that the water will not freeze. So that's why over here melting, it just needs small energy, yeah, melting temperatures, getting into here. So from there, we are now having water with 0 degrees. And when we have water with 0 degrees, so that was the ice melting. And now we have here the water with 0 degrees. That's what everybody knows when you're boiling now your tea or coffee. You're taking the water out of the tap, yeah, probably with 20 degrees or something, and then you put it into your water boiler, and the water boiler will use certain quantity of heat, certain energy here, to increase the temperature from, let's say, over here, 20 degrees Celsius, increasing the temperature to our boiling temperature of 100 degrees Celsius. So that's what's happening in the water boiler. So we getting up here, getting the higher temperature, and then we will see the water boiling. Soon the water is boiling, you will hear it. The first steam bubbles will come in, and then at a pretty close point over here, let's say the water boiler will be getting off. So it will switch off because you want an hot tea or hot coffee, and you still want to have hot water. You don't want to have steam over there, or all the point steam, yeah. So that's the amount of energy or heat, let's say, you will put in here to get your water boiling. In the power plant, let's say we have this part over here, which will happen in the preheater, and in the preheater, this boiling temperature is depending on the pressure. So the higher the pressure is getting, the higher our boiling temperature is getting. So for this example now, 1 bar, yeah, 100 degrees, our water is boiling. And when we have now the water boiler or tea boiler over here, and the tea boiler is not switching off, yeah, so we're saying, okay, we removed the safety out of it, yeah, so the water boiler will just go on. Then we're coming here to the vaporizing point, where, let's say, we have 100% water. So over here it's 100% water with 100 degrees Celsius. And then the vaporizing is starting, and we're getting more and more steam over here, where the steam temperature is also 100 degrees. So this point over here, 100% water. And on this point over here then, 100% steam at 100 degrees Celsius, and over here also 100 degrees Celsius. So we have no temperature change over here during the vaporizing process. So we're getting here 100% water, getting then inside here 10% steam, 20% steam, and so on, until we're having here the last water droplet is vaporizing, and then we have here 100% steam with 100 degrees Celsius. And from there, when we're still bringing energy or quantity of heat in, we coming to the so-called superheating. That's what we want to have inside our power plant. So the steam turbine normally only like superheated steam, because otherwise you have a risk that when the turbine is running, the temperature is dropping inside the turbine, yeah, you're getting through the stages, that the temperature is dropping, so that you're getting somehow here into the wet steam area again. So you have water droplets, and water droplets on a running turbine are of course really bad. So then over here, the steam in, yeah, so you have the superheating steam in. And what's interesting, let's say from the quantity of heat, when you're increasing the temperature from water from 0 to 100 degrees Celsius, you will need less energy than boiling the water or vaporizing the water from 100 degrees to 100 degrees. So this vaporizing process is using a high quantity of heat over here, and then the superheating process is again a smaller part, because here you're changing, let's say, the water into steam, and there you need much more energy for it. Okay. Questions from your side so far? Okay, then I would say we make a short break. I will check with my admin. Let's say 10 minutes break, yeah. And then after 10 minutes, we will go on with the next sheets, yeah. You can hear me, yeah? Just the properties are equal density. So the critical temperature is 374.2 degrees Celsius, and the critical pressure 221.2 bar Celsius. So when you go in a power plant above these values, you will not have the so-called vaporizing phase anymore. This wet phase you don't have anymore. So when you have water and bringing it above the critical point, let's imagine 250 bar, and you're increasing the temperature above the critical point, at one point you will have water, and then suddenly the water will change into steam. Without this long phase where you're bringing a lot of quantity of heat in, it will just go suddenly from water to steam. Has some advantages. We're using this normally in coal power plants, where you then, let's say, supercritical power plants, yeah, where we go with the pressure of 250, 300 bar from the feed water pumps, and then getting the high temperatures and have this sudden change from water to steam. the temperature is lower than the critical temperature, gases can be liquefied via pressure, yeah, above it is going on. And then we have over here the superheating. And the superheating, for example, we have here 80 bar, 380 degrees. So that's our superheating value, our steam temperature measured in the system. And when we go here now from this point here on top and say we're going straight down until we touching the, let's say, saturated curve for water, then we know for 80 bar, we are here at 295 degrees Celsius. So our saturating temperature for 80 bar is 295 degrees Celsius. And we have now 80 bar with 380 degrees Celsius. So we are superheated. We have superheated steam, and we have a superheating value from 85 Kelvin. These 85 Kelvin are important for we want to start up the steam turbine. There you need to have a certain superheating value in the X criteria for the boiler, and this value needs to be then normally above 20 Kelvin or above 30 Kelvin. Yeah. It's giving us a safety distance to the saturated curve. On the saturated curve, there could be still single water drops in. Yeah, so the last water drops are getting out there, and you are pretty near, let's say, on the border. Yeah, so you always have the risk temperature dropping by 1 degree, you're getting water droplets again. So what we want to avoid is that we're getting to the steam turbine. Somehow the piping is cooling down the steam by 1, 2, 3 degrees, yeah, and then we're getting directly water into the steam turbine. So what we're doing, we have a so-called safety margin in, and the safety margin is the steam superheating. The superheating, so we're saying we want there a superheating of 10, 20, 30 Kelvin to make sure we don't get water droplets in our turbine. And that's why here the steam superheating value, and it's just a calculation. Later on, during operation, you're normally 100, 120, 150 Kelvin superheated, so you don't have the risk anymore. But during a startup, it can be that you're landing here pretty near to the superheating, so the saturated steam curve, and therefore we want to have a certain gap over there, not allowing wet steam to get into the steam turbine. So the steam superheating, why are we doing this? So the work medium, our gas or steam, expands stage by stage in the turbine, and therefore pressure and temperature are decreasing. So this is what's happened inside the steam turbine. So during the steam turbine, the pressure through the turbine will decrease, and when the pressure is decreasing, temperature will also decrease. So when you're getting in this example with 565 degrees Celsius, 125 bar, and then probably on the outlet of the LP turbine, you're coming out with 29 degrees Celsius and 0.04 bar. So that's a pretty low value, and all the time, let's say you want to make sure that best possible the steam is still superheated. Because water droplets are bad for our turbine. Water droplets, you have the high steam velocity inside the turbine, and a water droplet would be like a bullet from a gun, yeah, so it will just shoot through the blades and will damage the blades. And this is what we absolutely want to avoid. So steam turbine requires superheated steam to avoid any condensation of steam. Condensation of steam is the creation of water droplets during the expansion process of the steam, and these droplets could cause erosion, damages, of the turbine internals. And the superheating, is steam temperature minus saturation temperature. So when you have in the system a value in, you're measuring your steam temperature, 380 degrees. The saturating temperature for this pressure, 80 bar, will be automatic calculated by the system. And then you will see on the HMI normally, okay, I have a superheating value of 85 Kelvin. And there are also one thing directly for the power plant. So as soon inside the power plant, wherever you go inside the power plant, when you have direct temperature measured, so you have a steam temperature measured, you have a water temperature measured. As soon these are direct measured temperatures, they will be shown in degrees Celsius. As soon it's an calculated temperature or differential temperature, like here, steam temperature, which is directly measured, saturating temperature, which is a temperature, and you're getting an differential temperature out of it, it will be shown in Kelvin. This has the big advantage for you as an operator, when you go in there and you see, okay, I have there 30 Kelvin, so it's not a temperature of 30 Kelvin, which is then minus 240 degrees Celsius or something. No, it's really an calculated value where you know, okay, this one is calculated. We make this to make an easy, let's say, difference between direct measured and calculated values, because when you would have here then steam superheating 85 degrees Celsius, then it would probably bring problems again, because you don't know, oh, is this now a calculated one or is this a direct measured one? 85 degrees superheating, this is too much, too less or too much or whatever, so that's why we have here the difference into Kelvin, so differential temperatures on a Siemens power plant are normally with Kelvin, and direct measured one with degrees Celsius. So here on the right downer side, we have then a saturated steam table for water. This is a table you can find in the books. You can find it on Google for every pressure. So there you have some values in here. So we're starting with this 1.013 bar. So that's the pressure we have around, temperature from the water or saturated temperature from the water. We have then 100 degrees Celsius, and we have a certain density of steam. So 1 kg, 1 liter of water is weighing 0.958 kg. And in most cases, we're saying then here 1 liter is 1 kg at these values, But when we go up with the pressure, when we go up with the temperature, then, for example, here 86 bar absolute, we have a saturating temperature from 300 degrees, and we see 1 kg of steam is just using, or 1 liter of water is just using 0.712 kg per liter, So the volume is getting lower, and the higher you go, you see it's getting even lower to 0.3, Critical point, 221 bar, 221.2 bar Celsius. We're coming here to 0.321 kg per liter. And this is, of course, a case when you go onto the power plant and you see then the pipes and the HP piping, because you have the higher pressure, you have then the lower density of steam. So you will have over here then the smaller diameter for the HP piping. So HP piping, higher pressure, lower volume in, yeah, or lower density in. So 1 liter of steam is just 0.7 kg, so you need less volume. And then when you compare it to the low pressure piping with the same amount or same flow through it, yeah, will have a bigger diameter. So when we go here again, evaporation, saturated steam temperature, and pressure, yeah, we have a pressure cooker, yeah, so 1927, the Secomatic, yeah, Seco by the company Sillet, yeah, was introduced into the market, and the pressure boiler is there to increase the temperature, and therefore, let's say when you for a cooking with higher temperature, you can increase or decrease, let's say, the cooking time. Yeah, so it's cooking faster. That's why it's called a pressure cooker or fast cooker. Yeah, you have there normally different ways in. So 1.4 bar would give you a temperature, saturating temperature of 109 degree in there, and it's going up to 2 bar. Yeah, then you're reaching the 120 bar inside the cooker, yeah. So it will boil your food faster than when you just boil it with a normal cooktop, yeah, which is open to ambient, let's say, which is not sealed, and then you're reaching the 100 degrees Celsius. Of course, important is on these ones the safety valve, because otherwise, at one point when the safety valve is not working, there were already accidents, yeah, when the cooktop is then flying around in the kitchen and hurting people, etc. So that is one way. Let's say we in the normal for normal boiling can increase the boiling times, and then the second case is, let's say, when the pressure is getting decreased, then the saturating temperature is of course also decreasing. So for when you go up to the Mount Everest, yeah, then you want to boil your coffee on top there because you're so high, yeah, your ambient pressure will be lower, and therefore, let's say the saturation temperature will be lower. And then in most cases, let's say the coffee is not reaching the temperature, so it will taste like not so good, yeah, because the coffee needs a certain temperature. And that's when you have here pressure going down and the saturating temperature is also going down. So one rule of thumb, yeah, describes that with a temperature increase of 10 Kelvin, the chemical reaction rate is increasing by 2 to 3 times. Cooking is finally a complex process of the chemical reactions, and therefore, let's say, fast cooking can increase the cooking time, yeah, and therefore, let's say, the fast cooker are sometimes welcomed here. So in general here now, the last sheet for evaporation and condensation, yeah, we have here now one time, let's say our heat over here, we have water in, boiled over here, we have steam coming out, and we have over here the condensation again. So we're catching up the steam. The steam is condensing again, and we have here 3 temperature measurements. So we're measuring one time the temperature of the water in here. We're measuring one time the temperature of the steam, and then we're measuring the temperature of the condensed steam, which we're catching up again. So the temperature over here, we see we are at 1 bar. So the temperature for boiling water would be 100 degrees. So just So this one would be 100 degrees Celsius. So that's our boiling water. So we are on the saturating curve, and then the water and steam mixture, the so-called wet steam area. So we are somewhere, we go back, somewhere between here and here. So that's when we see the water boiling, depending on over here, like we said, 100% steam, over here 100% water. So somewhere in between we are, but still temperature, that's most important, 100 degrees Celsius. So when we check on this picture now again, we see, okay, we clarified, we have here water with 100 degrees or water and steam mixture with 100 degrees. And now the steam is getting out. The steam which is getting out has also temperature of 100 degrees Celsius because we are still on the straight curve. And then when we condensating it again, condensating temperature will be also 100 degrees Celsius. So all three temperatures are equal because we are still here on this phase. Steam is getting out, it's 100 degrees, it's not getting superheated, we don't have any energy source in here which can heat up our steam further, and over here we condensating it and bring it down. So now we're putting or close the glass over here, putting water in. So we have here now steam with, yes, Saif.
Mr. Sebastian, at evaporator, when you evaporate this water must be less than 100 because it's evaporator steady. You know that at any at any evaporator at any evaporator water must be rejection the temperature from the 100 to maybe 70.
No.
Oh, okay.
This is not the case because let's say it's pretty simple. We are here on this case, and we can also see it. Probably give me 1 second. I open up another sheet for you, which is not in the presentation, but will make it hopefully more clear for you. Just give me 1 second. So I think you will see this one now. So this is the so-called TS diagram. And the TS diagram is another form, let's say, to show the saturating process or the process of water boiling, vaporization, etc. So it's the temperature and you have the entropy of the water, and the entropy is giving with this S, yeah, in kilojoule per kg per Kelvin, yeah, times Kelvin. This is the entropy in. And when we see here now in this example, so we're taking here one time the water, yeah, taking it out of the tap, we're going here to 100 degrees Celsius. That's in red is our saturation curve. So here is written X value. X is our vapor content, yeah, or steam content in the water. So over here, X value is 0, so we have 100% water. And over here, X value is 1, so we have 100% steam. So when we're getting here into the TS diagram, we're getting to our 100 degrees again. So 100 degrees, we have here on the left side, 100% water. And now for the evaporation, yeah, vaporizing of the water, we giving more energy in, and we're getting now to this point, 0.1. So we have over here 10% steam, 90% water. So there are some bubbles in already. But the temperature is not getting down to 70. The temperature here is constant. Temperature is constant. So when you're getting in here, you still have 100 degrees. And you have water at 100 degrees, and at the same point, you have an amount of steam with 100 degrees. And at this point, you have around about 10% steam already in. So 90% water at 100 degrees, 10% steam at 100 degrees. The temperature is equal. You're not going here somehow saying, oh, evaporation is starting and it's going down to 70 degrees and then going up again. This is not happening. It's a physical process and it's happened at the same temperature. So there's no cooling down there for the evaporation. And then let's say it's happening at the same temperature. So that's what happened here at 100 degrees. 10% steam, 20, 50, 70, 80. And then over here, we're coming out with 100% steam. Our X value, our vapor content is 1, so 100%. So there is the last water droplet gone. And that's what happened in our evaporator. In the evaporator on the power plant, it can be that you're getting water out with 90% in some startup cases, 80%. And these ones will be separated then inside the drum. But the temperature will be still saturating temperature in there. So there will be no cool down here to somewhere over here where we're saying here we have steam now with 70 degrees or something. This is not happened. It's happened all over here vaporizing at the same temperature. And the same thing then later on when we're coming to condensation, we heard it before already, condensation, there is energy getting free, yeah? So here we need to put energy in to get it to, let's say, vaporized. And when we see here, this is from the steam turbine outlet, so LP turbine inlet to LP turbine outlet. And now we're getting here on the outlet steam with 0. What we have 32.9 degrees, so 0.05 bar. So that's over here, 0.05 bar. There we have a saturating temperature from 32.9 degrees. And now the same process happening. I have here steam, which is here already in this example in the wet steam area. So I have steam with water already. I have here 85% steam. So 15% water droplets are already in here. For a turbine, that would be too much. Yeah, saying it would be too much. Normally, we want to be over 92, 93, 94%. But then condensation. So here I have steam, condensation happening all on the same 32.9 degrees Celsius. There will be no subcooling or something on the condenser. And then it's getting to here where I have then 100% water or condensate again with 32.9% degrees Celsius. And from there, I'm getting back into condensate pumps, increasing the pressure, bringing it to the system again, and that's what's happening. So I don't have any subcooling or something inside the evaporator. This is not happening. So, Saif, I hope that's a little bit more clear now for you.
It's okay, Mr. Thank you.
You're welcome. So this is really a point where you need to, let's say, accept it because it's physics, you cannot change it. And so that's just how it is. You don't have any subcooling in there on the evaporation, and you also don't have any subcooling in there on the condenser. That's a physical process which happening, you'd say, you're changing from water to steam by the vaporizing with the same temperature. And in the same way on the condenser, you're changing, let's say, from steam to water at the same temperature.
And T3 from the evaporator to condensate.
Yes.
Same temperature?
This is the same temperature because you're changing again just the condition of the steam. So the steam over here will go, when we go back, we'll get back here to this point. So it will be 100 degrees on the first moment, but of course, when you take it now, let's say extremely accurate, then this column should go here on the top where, let's say, the steam is condensating, so it's changing its phase from steam to water. When it's dropping down here now, there will be probably already some interactions with the air. So the temperature, when you take it totally accurate, let's say you need to make this one, let's say to this point over here where it's coming on top. And let's say the droplet over here, when you say this one, probably is already 98 degrees because there's some exchange with the air. The air is probably cooler and it will cool it down. But so far, I don't want to go. I just want to say when the steam, so the steam is coming out here and over here on the face, it's condensing again. That's all happening at the same temperature. And that's the process we have over here. So this process, 100% water, 100% water, vaporizing, steam is getting out, and then getting to water again. This is all happen on this 100 degree phase. So that's all the same temperature. Then, of course, when you're dropping it down here and interaction with the air, then the temperature from this droplet will be probably a little bit colder already. That's the same thing. I mean, this example you can try with a tea boiler. You have the tea boiler, you have the steam coming out. When you put a temperature measurement inside the steam, you will see it's 100 degrees. And when you put then a glass mirror or a cooktop or something on it and the water is there, it will be also the water in the first moment when it's there again will be 100 degrees. And then depending on your cooktop over here, when this one is colder or it will cool down with the ambient air, then the temperature will be getting cold from the water again. But in the first moment, when it's changing the phase from steam to water, this will be 100 degrees. Saif, is this understandable now?
Okay, thank you, Mr.
Okay. So that's why I said here, the temperature is the same. You're just changing the phase, but the temperature is the same. So then we have over here, when we close now this bucket, putting temperature in, yeah, still heating up, we're coming to 120 degrees. So what will happen? the pressure in the pot will increase. You will still have water in here, so the pressure is increasing. You have over here 300 degrees, pressure is increasing, yeah. When you have here getting down to 30 degrees Celsius, so you have a closed part in here, so then you will have here a certain vacuum inside, yeah, so the temperature will go down, and that's then what's happening inside the condenser. So you will have a certain vacuum in here that you're getting the 30 degrees. So we saw before 32.9 degrees Celsius, round about 0.05 bar. So something like this you will have in here. And then 400 degrees, of course, is then superheated value. So this is just examples in here. There I will not go too far with this one. So that's now the basics, let's say, from the evaporation and condensation. Important is, like Saif asked, evaporation is always happening at the same temperature, and also condensation. And it's both depending on your saturation or evaporation temperature. That's the important part. So in the power plant, when we go back, let's say, to the first page over here. So we say we have here on the power plant, we have somewhere in here the preheater, which is just warming up our temperature. So that's this phase here over here, up to probably 3, 4, 5 Kelvin under the evaporation temperature. So you have there a certain pressure in, and then let's say you say in the preheater you don't want to have evaporation in. So or in the economizer, yeah, like it's called in the boiler. Economizer should be always staying underneath the boiling temperature, because it's not designed for it. An economizer or preheater is designed for water, just from the volume you're bringing through there. And then when you go, when we go further, we're coming here to the evaporator. We have the drum, we have the evaporator, and the evaporator is from the design designed for the evaporation process. Because what's happening, I have a water volume in there, and the water is steaming out. I'm getting a much bigger steam volume in there, and the steam volume need to be there so that the piping can handle the steam volume. And that's what we have inside the evaporator. So the evaporator is designed for it. There, the evaporation process can take place. It should not take place in the economizer or the preheater. It should take place in the evaporator. So we need to make sure the temperature we're getting into the evaporator or out of the economizer need to be below the boiling point. And then in the evaporator, the steam will be produced. And when we're going then further to the superheater, where we're superheating our water, so from here to here, there, of course, we want to make sure that we're not getting any water particles in there. So from the evaporator outlet, it will be like 1-2 Kelvin above the boiling temperature, so slightly superheated by 1 or 2 Kelvin, to make sure that there are really no water droplets getting into the superheater. Because when these water droplets would get into the superheater is just designed for steam and not for the evaporation process. So economizer, just water; evaporator, water and steam; superheater, just steam. Okay, so that's for this part now. We have here the phases. Are there questions from your side?
No, thank you, Mr. Sebastian.
Okay, then it's, I think, 3 minutes to 12. Then I would say we making the lunch break for 1 hour, and we meet again then at 1 o'clock.
Okay, we go back on 1 o'clock.
Okay. Thank you. See you then at 1 o'clock.
Welcome, Mr. Sebastian.
Thank you. Bye bye.